So my name is Rocky Dunlap. I'm the manager of the Earth System Modeling Framework core team, and I just want to say thank you to the core team members who are co-authors on this presentation. We have a distributed team with people at National Center for Atmospheric Research. There's people at NOAA Global Systems Lab and University of Colorado Ceres. We have team members at NASA and also at the Naval Research Laboratory. And so ESMF is a multi-agency organization and a distributed team. So thanks to the team for putting together the software, and just appreciate this opportunity to present to you. So for my talk today, I'll give us just a quick overview of ESMF and different ways of using ESMF. Then I will spend a little bit of time on the NUOPC interoperability layer, because I think that's one of the more unique parts of ESMF and how it provides interfaces for coupled models. I will show some kind of preliminary study that we're doing on ways to connect coupled data assimilation systems with ESMF and NUOPC. And then I'll give an update on the last ESMF release and then what we're working on for the next release. So ESMF is a high-performance software infrastructure used in coupled earth science applications. And right at the beginning, I just wanted to point out that there are several different ways of using ESMF, and I've tried to categorize them so you can wrap your head around the different ways to approach the library. On the left, ESMF can be used within a modeling system as the coupling infrastructure. So in this case, you have a driver level, you have some number of components which have interfaces on top of them, and then you have the ESMF library at the bottom providing some communication infrastructure and other pieces. Another way to use ESMF is to just leverage the regridding capabilities. And you can do that either through the command line. If you're working over NetCDF files, you can just issue a ESMF regrid command and remap from a source NetCDF file to a destination. And you can use all of the interpolation options that are built into ESMF, are all available through that. The other thing you can do in the offline case is use Python. So the Python library is just a wrapper on top of ESMF. It's all using the same underlying remapping software, and you can bring it into a Python script as part of your workflow. And then the last piece we see is that people building more advanced tools such as preprocessors that need to combine data from different places linked to ESMF as a library. And so for this talk, I will pretty much only be focusing on the coupling infrastructure part. So I mentioned the NUOPC interoperability layer. That NUOPC acronym stands for National Unified Operational Prediction Capability. And it came about as an agreement on an API that could advance interoperability of different modeling across different modeling centers. And so the NUOPC layer has within it these 4 generic components. And so this is part of the ESMF library. If you download it and install it, you automatically get the NUOPC layer with that installation. And the idea of the NUOPC layer is to give the user, to give you a set of generic components that already have an implementation that you can extend with only the parts that you need to customize. So this is very much like an object-oriented style of operating or programming. So there's the driver, a model, a connector, and a mediator. So these 4 types are able to be deployed generically and used in a whole array of different kinds of coupled systems that I'll go into detail about each of these. So the driver layer within ESMF and NUOPC sits on top of a coupled system, and within ESMF you are typically compiling a set of components into a single executable with one top-level driver. A nice thing about this approach with the driver is that the run sequence can be specified in a small user-friendly text file, meaning there's really no Fortran code that you have to look at, which is describing the sequencing of the components. And I'll show you an example of one of these run sequences, and it can be modified. The run sequence can be modified without even recompiling the code. So you have a lot of flexibility. Once you have an executable, you want to run several different configurations for different test scenarios. You can do that without even rebuilding the code. Within the driver, the model components are included or excluded during initialization. So that's a runtime option, and that allows you to exclude or include during the initialization certain components. And then drivers can be easily extended with new components, and there's no limit here on the number of components supported, and there's no hard coding of kinds of components. So for example, you could have two ocean models supported under the same driver to be able to swap between them if you're comparing components with each other, for example. So the diagram on the right is an example system. This is with NOAA's Unified Forecast System. This is a subseasonal to seasonal, a configuration of that particular application. So this is an example of the run sequence syntax that I mentioned. You'll see in this case it supports nested loops, and you have a time step indicator. So the at 1800 on the top is an 1800 second coupling interval, and the at 600 is a 600 second coupling interval. So this particular run sequence has a slow loop on the outside where the ocean component is coupled, and then a faster loop on the inside where the atmosphere and ice components are coupled. Within the syntax, you see the arrow notation. That is an indication of the connector, execution of the connector, which is the green arrows in the diagram. And the connectors are, I'll get into it in a minute, but they're basically providing communication. And you can see in this case, the run sequence is parameterized, so you can tell the connector what you would like it to do. So for the mediator to ocean remapping, this is a redistribution operation. You can also see that multiple phases are supported, particularly for components like the coupler or mediator in the middle, where there's interaction with each of the other components. There's a need to have separate phases, and so those are all user-defined phases, and you could easily extend the number of phases that you need depending on the kind of coupling protocol that you're setting up. So on top of each component, under this kind of architecture with NUOPC, you need to define what we call a cap. And this is an interface layer. It's non-intrusive. We tried to design this such that you don't have to make a lot of changes inside the model code. Typically, the cap is a single Fortran file, Fortran module. It may be several Fortran modules, but it's not a large amount of code. And the idea that we try to promote is that the cap, or the interface for each model component, lives inside the repository of that model. And the advantage of doing this is that once a cap, NUOPC cap, has been written for a component, it should be the only one that needs to exist, and it should be shared across any organization that is using that component in their system. And this has a huge advantage of saving a lot of resources and increasing productivity, and also a lot of advantage of bug fixes, since in many cases for codes that are widely used, for example, I give an example here of the MOM6 ocean model where the cap is. There's several different institutions that are coupling with MOM6, and reusing that same interface has really given us an opportunity for lots of developers to be looking at the same code, improving it, finding bugs, and then the community as a whole really benefits from having a more robust coupling interface to each of the models. The connectors, I think, are one of the most powerful parts of the NUOPC layer. They are the green arrows in the diagram, and they provide communication and remapping between components. Connectors are generated automatically by the driver, so there's actually no user code that you have to write. They're entirely parameterized components. At runtime, the connectors are responsible for figuring out the field exchange based on the set of standard names used in the imports and exports from the constituent components. So there's no hard coding of what fields are actually going to be communicated between the components. That's determined at runtime, and that's to allow a lot of flexibility in the system, because during initialization, you're actually establishing what needs to be communicated. And if a field is not needed, it doesn't have to be included, so there's no redundant communication. The connectors leverage the ESMF regridding and redistribution behind the scenes. So you get all the interpolation options that are built in with ESMF. Connectors also have a negotiation phase at the beginning where the most optimized connection is determined during initialization time. And that can be all the way from completely sharing everything. So shared grid, shared field, shared memory between the components. So that's a very tight coupling to a more loose coupling where the grids between the components are completely different and the processor sets are completely disjoint. And so you need to remap, do the interpolation, and also reshuffle the data and redistribute. So there's a whole gamut, there's a whole spectrum of different ways that can be negotiated, and the connector is responsible for figuring out what is the most efficient way to do it. One other aspect of the connectors, which is very powerful, which I think is also pretty unique, is this ability to transfer grids between components. This is really important, in particular when you're using a kind of mediator component where it itself doesn't really own a grid, but is dependent on the other components to give it a grid. And so during the initialization protocol, a component can say, I don't have a grid, but I need a grid. And the connector is responsible for transferring that grid over in parallel, and then that same grid can be reestablished on the destination side. The mediators are the final kind of generic NUOPC component. And this is a kind of component that allows you to put coupling code that is related to multiple model components that are communicating into a kind of hub and spoke architecture. So this is the kind of classic example of a flux coupler where you have multiple components sending data in. And so this, if the connector is option doesn't satisfy your user requirements, the next step is to write a mediator where you have a lot more flexibility in how the fields are merged and mapped. This approach also supports incremental building up of coupled systems, because the same interface can be used to introduce what we call data components into the system, where you don't have to run an entire active prognostic component. You can introduce forcing fields into the coupled system without making any changes to the coupling interface. So this is a huge advantage to speed up development time while you're building the system, since you only need to run one or two active components and you can force the rest from file. One of the questions that we're currently studying right now is how to connect this architecture into a data assimilation system. And at this level, we're mostly thinking about the architectural design. As many of you know, one of the capabilities needed by the DA system is to have control over the forecast model. And so there's different ways that this architecture could be set up. One approach would be to have separate caps that the DA system uses to control the separate components: ocean, atmosphere, sea ice, in this case, in the mediator, and that's sort of supposed to be represented by the purple diamonds. But there's a lot of disadvantages to this approach, because you lose the sequencing that the driver provides. And so the DA system, there's a risk here, will have to reproduce a lot of the same capability that's already included with the coupled system. So the approach that we are currently thinking is the best way to do, and we're prototyping within the NOAA's Unified Forecast System, is to actually have the DA system sitting on top and accessing the coupled system through the driver. And when we do it this way, we introduce what I'm calling these vertical connectors. And this means that the DA system is able to access the model state in the individual components and the coupler, and to request it at different times. And so this allows us to keep the run sequence of the coupled system in place. And that can be sort of reconfigured as well if you want to turn off feedbacks, while the DA system only has to have one connection into the system. So we think this is the most promising approach and the right way to architect DA connected to NUOPC. This is just an example of the run sequence showing how we can return in the middle of the run sequence up to the DA layer so that that layer can run and then update the model state and then come back into the run sequence. And to accomplish this, we've added an external interface to NUOPC, which provides some hooks for the DA system to connect in at key points during initialization, run, and finalize. And I put a link there on the reference manual if you're interested in how this external interface to NUOPC works. And then finally, I just won't go into this because I know we're short on time, but I just wanted to include here the some of the major items that were part of the last release. That's 8.0.1, which was released May of 2020. And these are the major development priorities that we have for version 8.1, which is expected in March. And this is not everything, but these are the major tasks, and the full list is available at the link there. So I apologize I wasn't able, for time's sake, to go into detail on those, but wanted to get those out there to you. So thanks very much for your time.